This is the president. This is the president. I want to see you break into break into break into white by number two. By number two, by number two, certain by number two. Public all the run times, all the run times, all the run times, all the run times. Do it for the USA.
Hopefully you enjoyed this week's music video, proudly brought to you by the President of the United States. And we are back for the third last week of class. I know semester's almost over and we're coming to the end, but we've still got some exciting things to learn. So as with the start of every week, this week is America themed, so we have a new historical figure, and this is Commodore Grace Hopper, U.S. Navy Rear Admiral, born 1906 to 1992. And she was the developer of machine-independent programming languages. So you'll remember in some of the classes I've shown you like a little bit of assembly code that's like the code that the machine actually is running. Well, you could create a programming language that's just like that for your specific machine. And in fact, for a long time, that's exactly what was done. Every computer had their own assembly language that you needed to learn. Grace Hopper's idea was that instead we should come up with another program and another programming language, and our other program called a compiler would convert the programming language we wrote into the assembly language for the respective computer. That way, you didn't have to worry about what the details of the assembly language of the machine were for the machine that you wanted to run the program on. You'd write your program for any computer, and then the compiler would convert it down to the assembly language for the computer on which it was going to run. She was one of the primary inventors of the compiler altogether and did a lot of the heavy intellectual work that was necessary to conceive of them. And she was also adamant that one day we would program computers in English, and today we are closer than ever for the first time to her dream. So she wrote the compiler for the A programming language, so that came before B and C. And she also influenced COBOL, which is a language that actually, if you learn, you're likely to make a lot of money because a lot of very old banking systems run on COBOL, and there are not very many COBOL programmers out there. So if you are the one person who can fix an old bank's COBOL program, you can fetch a pretty high premium in your salary. So going back to where we were last week, we had our discussion about my friend the ape here, who had a bunch of questions about his descendants. So in this case, he wanted to know which of his descendants lived to age 13, and we talked about using an array of structs to represent this information, and this was really a bit of revision, because the best way that we had already in the class to figure out where the number 13 was in this set was to sort them. We talked a lot about how to sort things if you don't know how to compare them. So you can write your own sorting function and use a function pointer. And then we'd do binary search over the results to make it more efficient, to give us a log n runtime for every time we wanted to do a search, as opposed to an n log n runtime for our sorting. But this is our problem. In real life, normally we don't just have one set of items that's static. Very often we have data that keeps getting added to and gets removed to. So we might want to add things to our array or remove things from our array. So if we want to do this with, let's say, some monkeys are born and some monkeys die and they live to different ages, but we still want to do the same fundamental task, then we've got this issue, because one of the things that we might think of doing is sorting them and then doing binary search, but we add something new and we have to sort them again because that new item is going to be out of order. So instead of being n log n once, it would be n log n every time a new item comes in. So let's say we have m items, or let's say k new items coming in, then we'd have to do k times n log n plus k log n. And the reason is because every time we add a new item in, we're going to redo our sort and redo our search. So not so great. Our structure was all right for the basic version of our problem, but we're going to need something a little better. So Andy, do you know what that's from? Yeah, Smash Brothers. So we have our binary tree, which is going to be the focus of today's lecture. But before we talk about binary search trees, which are going to be the thing that we actually use to solve the problem, let's just talk a little about trees in general. So you'll notice this tree is a little funny because that element 20, that's what we're going to call the root. And most trees do not have their roots on top, but as computer scientists, we tend to always flip them that way and call that very first item the root. Then you can have any number of branches splitting off of it, any number of children nodes, we call them. So the root has children, and at the very bottom of the tree, we have leaves. These are the items which have no children. Now, in this example, what I've depicted is called a binary tree because every parent can have at most 2 children. Every node can have at most 2 children. If it has 0 children, it's a leaf. If it has no parent, then it is the root. That's the one at the very top. So this is a binary tree because each one can only have 2. And we can represent this using a struct. Now, Hamish has volunteered to be the star of the show for today. So as soon as we get our microphone on, he's going to take us through some of our work around trees. So let's say we are making a struct for a tree. How would you design the struct?
How would I design the struct?
Yeah.
Type def struct,
Type def struct.
then the curly brackets.
Oh, I better turn the AI off or it will ruin everything for us. Well, it should be disabled. I don't know why it was completing for us anyway. We'll give it a go.
A node.
So that'll be the name of the struct. So we could do it like that. Good idea, because every element of our tree is going to be a node. What do we want in our node?
We want to know where the node points to,
Yeah,
its children.
good. So for a binary tree, how many children do we have?
2 children.
Yep. And what's a reasonable name for them?
Pardon?
What's a reasonable name for each of the children?
Left and right.
Yeah, left and right. So let's do that. And that should be a pointer.
Mm-hmm.
So worth having anything else in here?
Its parent.
So that might be actually useful. That's not a bad idea, but for today, we're not going to have a way to get back to the parent. You'll just have to keep track of it if you want.
Mm-hmm.
What else do we need? What did we have in our linked list nodes?
Our data.
Yeah.
Yeah.
And remember, because we're going to need to remind the compiler what a node T is. So what we should actually do, type def struct node T, so that when we use node T in our recursive data structure, because it's referring to itself, that it's already there. So that was a great job, and that's exactly what we needed. So Hamish is on a roll so far. So now, what is the runtime to find the oldest monkey, assuming that we put them all in a tree? So we'll go slowly. Don't just shout it out right yet. So let's say we're starting at the root. The root, just like in the linked list, where we started at the head of the list and went from there onwards, we're going to do the same thing. So how do we find the monkey whose age is 13? What's the first thing I should do? All you can see right now is the root.
We need to traverse to either the left or the right child.
Okay, so let's start with on your left.
Yeah.
All right, okay, what do we do next?
Do the same thing and go to the left.
Okay, there is no left in this one. The dotted lines refer to no left, so there's just a right. We're on right.
And then left again.
Okay, now what happens?
Now that we're both pointing to nothing, we go back to the root.
And remind me, what's it called when you have a node that doesn't point to anything in a tree?
A leaf.
Yeah, that's a leaf.
Yep.
Okay, so we have to go back to the leaf's parent because there was nowhere else to go. Okay, now where?
Well, we cannot go to the right.
Yep.
So we have to go back to the root.
Yep.
And then we've already traversed left and right, so we go back to the root.
Go back to the root. Now what?
And then to the right.
Okay, and I won't make you talk you through. So now we take the left. There's only a right, but no more options. We backtrack. And we're done, in theory. 13 is not in this list. How long did that take us to find out? Assuming there are n nodes?
That took us n times.
Yeah, that took us O of n comparison. So we had to go through the entire tree. This seems worse than binary search, right? Remind me how long binary search takes?
Log of n.
Yeah, log n. So O of n is worse than log n. It's unclear why we're doing this. This is even slower than linear search because in theory, counting the number of backtracks, it's going to take us a couple of extra steps to go back. That's really not very good. So much slower than binary search. But binary search required something, right? Do you remember what it was?
That the list or array you're traversing is sorted.
Okay, yeah. So let's see if we can do something similar, impose some kind of structure on our tree, on our binary tree, to give it that same kind of sorting property. So the idea here is going to be to impose a partial ordering on the tree. We're not going to worry that every item is in the exact right place relative to all of the others. In fact, what we're going to do is something a little similar, a little different, and call it a binary search tree. And the property that we're going to look for is this. We want, for any given parent, everything on the right should be bigger than or equal to the parent, and everything on the left should be smaller than the parent. So let's look at an example of our binary search tree. Now remember that word in here is the key difference, search. That means that we're imposing this property on our tree. So now I've reordered things such that we're now in a binary search tree. If you look at the root, everything on the left of the root is smaller than 20, and everything on the right of the root is larger. So now what we can do is we can try some operations on it. So for example, let's try to find the runtime. Let's try and find the oldest ape and calculate the runtime. Okay, so what do I do to find the oldest ape?
So to find the oldest ape, well, we know that our parent root is of age 20. Therefore, the oldest, because he's in like the middle, it's got to be on the right, the larger side of the tree.
Yeah, so we're looking for something larger than 20, so we look to the right. So let's go to the right. Have we found the oldest ape yet?
No, because we know there's something still to the right.
Okay.
So we search to the right.
So search to the right. Have we found the oldest ape yet?
Because the right pointer is pointing to nothing, then we have found the...
Yeah, because we know that whatever is on the left, by virtue of the fact that this is a binary search tree, the rule is that anything to the left must be smaller than the thing we're currently looking at, and so we found the oldest ape. Okay, let's try something else. Let's try find the ape who is exactly 22. Okay, what do?
We go to the right.
Wait, explain that to me. I'm a bit slow.
So 22 is larger than our parent, 2 is 20, so therefore we go to the right.
Okay.
22 is less than 30, therefore we go to the left. 27 is less than, 22 is less than 27, so we go to the left. And now 22 is equal to our key of 22.
And so we're done.
Yeah.
So what was the runtime here? Do you have a sense? What is the most number of steps that this could have taken us?
The most it could have taken is if it was 21.
Yeah.
Yeah.
And how many steps would it take us to get to 21?
4.
And is 4 related to n in any reasonable way?
No.
It isn't, but it is related to something. It's related to a property of our data structure. Can you take a guess at what property that might be?
The height of the tree?
Yeah, the height of the tree. So the most number of steps it could take us is however far down the lowest item is, because that's the maximum number of steps you could take. So if we went right and then left and then left and then left, and then we got to the bottommost leaf, that tells us the most steps we could have had to have taken. So the runtime here, we're actually going to parameterize in terms of the height of the tree rather than just the number of elements. Because unless we know something else, some other information about the connection between n, the number of elements, and how those elements are arranged, we're not going to know exactly how many steps it's going to take. So in this case, I'm going to label my tree 1, 2, 3, 4, 5. So 1 is the very top, 2 is layer 2, 3 is layer 3, 4 over there, and then 5 at the bottom. So at most, it's going to take us 5 comparisons because we're going to compare with the root as well. So it's not just how many steps down from the root, we're also going to count our comparison at the root. Now, I'll just tell you right off that for a random set of elements, well, actually, what do you think the height of the tree will be for a totally random set of elements on average?
Yeah, I'm guessing it could get pretty big.
If you're going to average it out, let's say we have n elements. How many layers will the tree have? So what we're going to get, assuming that our elements are really distributed in such a way such that our tree becomes even, we're going to get this log n average case time. And if you imagine all the different ways we could construct the trees or search for something in a random tree, this is a very hand-wavy version, but if you think about it, half the time the tree will be on the longer than it should be, half the time it'll be the node that you're looking for will be on the shorter than it should be, and if we kind of average that out, the middle point is really that log n where everything's perfectly distributed. So you can do a proper proof for this. We're not going to do it in this class, but that just gives you a way to kind of think about it in your head. So we can use this same technique to find any value in our tree. Now, what is the worst case runtime for finding an item? Is that Pranav I can see back there? Yeah. Why is it O of n? So if everything is on one side, what do you call a tree that only has one branch? I heard someone say it. It's a stick. I mean, it is similar to a linked list, but we're going to call that a stick because we're in tree land now. So this is a stick. All the elements are on one side, going from smallest to largest here, and so this will give us an O of n runtime. So we don't want that. So this is where you have n items and you get a height of n, and so our worst case runtime is going to be O of n for a stick. So for a random input, the average depth that we're going to have to go down into the tree is just going to be log n, but we can't do this randomization process effectively unless you know all the elements at the start. So what this means is we're going to open up a whole can of worms in future classes about how to design a tree such that it gets you to this log n point most of the time, and it's really rare that you're going to end up with a stick, or in such a way that it automatically reconfigures itself such that you have better guarantees. And that's a larger area of research that is still active today. So this would get us our worst case log n search if possible, where we have balanced trees that every time you add an element, the tree reconfigures itself so that you still get that log n depth, which would be if the tree was complete and if the tree was balanced. Let me say that again. The tree is balanced where you don't have like one side of the tree going to a greater height than all the others. Now a tree we call complete if all the children have both of their pointers filled and all the leaves have nothing. So it's where you don't have any like dangling leaves out the end. If it creates this like perfect looking structure, then we're going to call it complete. So now it's your turn. With the person next to you, I want you to do the following two things. So starting from a node T of the root, find 42, sketch out the pseudocode for this. And you can do either the iterative method or the recursive method. So whatever code you can use, I want you to sketch out what the code would look like. So you've already seen me kind of do it. I want you to sketch down on a piece of paper or on your laptop or whatever the steps that you would take. Okay, coming back, we have a volunteer who's going to tell us, you want to do the recursive solution?
Yeah, way is working.
Okay, so let me find, let's do the recursive solution in here. And it's okay if it's just pseudocode. So we will call this search, and we will give you the root. Okay, go ahead. With the warning that this might not be perfect C code because that's not what we're going for. We just want to design the algorithm. I'll give you the code for it after.
So check the right node if it's equal to 42. If not, just return itself. Is it working? I don't know.
So what was the idea? Talk me through it again.
So every time the function will check the right side node if it's equal to 42. And if not, it return itself and check left node.
Okay, well, only checking the right side. Oops, I've already made an error there. And let's also say that's the number we're looking for example. So if we just check the right side, then we don't know. It might be on the left. So that's probably not going to help. Which node should we always check?
Well, if the root is 20, we should check the right-hand side because it's always on right.
Yeah, so we should always check the root. And we can imagine in our algorithm that whatever node we're currently looking at is like the root for all of its children. So we should always check the current root. Because we can, by process of elimination, we can say, okay, like just imagine that you ran the algorithm a little bit before and now you're at a new node, and now you're at this node, that's your root, because you haven't found it yet. And so from the current node, we should first check to see if the current node is the one we were looking for. So let's do node t star, and then we can do something like, so this is the case in which we've just found what we're looking for. If we didn't find what we're looking for, what do we do?
We check the right node.
Why not the left?
Because the binary tree already being sorted.
So remember, it's not perfectly sorted. We know that everything to the left is smaller and everything to the right is bigger, but we don't know, our number could be larger than 42, for example.
So you have to check if the right-hand side node is larger or smaller than 42.
So else if it's greater than 42, which side should we search?
We should search the left side.
Yep. And otherwise, what do we do?
If it's smaller than 42, have to return the right-hand side node.
Now, you'll notice that my coding style here is trying to keep it terse, and the reason I'm doing this is just to show you how short it can be. But if we were to write this out without our trap of doing these one-liner things, we could write it out like this, and it will still look pretty simple. Right, and you can see we only have three cases. Either the thing that we're currently looking at, the root, is equal to 42, or yes?
What if 42 is not where we're searching?
Yeah.
Check for nulls.
So we need to check for nulls as well. But this is assuming that it's in there. But that is an excellent point and something I should have actually said earlier. So if we're going to write out the full version, we would do another statement in here, and I'll just write that out for you as well. Why is it unhappy with me? There were the wrong number of spaces. There we go. And not P left. And then that solves the problem for us, because now we've actually checked if a child on that side exists. Yes, Toby?
It is now, because when we're comparing now with the internet, single trinity x, library is always smaller than 42. So to optimize, we might don't need to check if it's smaller than 42.
We don't need to check which?
Because like now is I think x is 0 or 1, which is very small number. What is compared with the internet?
So this is left and right. Left and right are pointers, and that's as opposed to comparing data. So the data element is the thing that we want to know if it's 42 or not. What we're searching for here is checking if that pointer exists. Yeah. So we're not actually checking the value of those nodes, we're just checking to see, does it actually have a left child? Does it actually have a right child? Which is what we're doing there. Yeah, at the back. What's your name? Owen.
Search takes 2 inputs, so it doesn't.
Oh, thank you. Search takes 2 inputs. That should be number, and then we can do number here. That's a very good point. So this is instead of just searching for 42, we can search for any arbitrary number. I got it right now? No more bugs? Okay, that is the danger of live coding. But I think now we have an implementation that is relatively good. And so if I go back to my slides, we can see this is more or less what I put there. This is one where we're just searching for 42 specifically, rather than searching for number. We can also do a version of it that is iterative, that looks pretty similar, except all it does is it has this while loop that is going through the left and the right. Yes, Alistair?
Just a linear search. What search is this?
It is a search through a binary search tree. It's neither linear search nor binary search. Yeah, I don't think there's a special term for it other than searching through a binary search tree. It's a new algorithm for us. Okay, so now that we know how to find something in it, let's talk about how we actually create these. Now, let's assume that we are going to start with a root that already exists. So you've already created the root node in some other function. This function is not going to handle the insertion of the root. And again, here is pseudocode, because now we're at the point in semester where the C code is important, but you as a class should be able to convert from a pseudocode description back into some C code that actually works while fixing some bugs, the same way that I had to fix some bugs while going along. So the first thing we want to do is we want to check, is the item we're trying to insert bigger than the root? If it is bigger than the root, then we're going to have to put it somewhere on the right. And we keep doing this process over and over. Is it bigger than the thing we're currently looking at, to figure out where in the tree it should currently be? So if it's bigger, then it goes on the right. If it's smaller, then it goes on the left. And so this is a recursive algorithm, because remember, the way our tree operates is every node is just like the root of its own subtree. The subtree being all its children and all its children's children and all their descendants, etc., etc. So it makes sense for us to think about our algorithms in a recursive way, because they're going to operate on essentially the same data structure, just a slightly smaller version of it. So let's look at this in a visual example, because it's often hard to kind of get the hang of this just looking at the code. So here we have our binary search tree from before, but I now want to insert 28. So which direction do I go? Where is the microphone? Microphone, do you want to pass it back one row? Is it Sharon behind you? Yeah, pass it to Sharon.
You would need to go to the right.
We go to the right because 28 is bigger than 20.
28 is less than 33, so you go to the left.
Yep.
Then 28 is bigger than 27, so you go to the right.
Go to the right, and we're going to actually need to create a new node there to put our 28 in. Now let's do the same thing with deletion. And again, I'm showing you code which is assuming that we're not trying to delete the entire tree. So this is simplified just to give you a sketch of it, and you can work out the case where you do allow for root deletion as we go along. So the first thing you want to do is find the parent of the node that you want to get rid of. Once you've done that, what you want to do is you want to back up the copy of whatever was on the left of the parent, and then first check if the node is childless. So the node is childless if the thing on the left is a null pointer and the thing on the right is a null pointer. So no children, it's childless, and you backed up whatever was on the left before, on the left of the parent. So if the element that you're looking at, that you're trying to remove, is childless, then it's pretty easy to delete because you're just going to lop it off the parent. However, if it has children, we're going to need to reattach those children to the parent appropriately. So let's try that out. Let's say we are trying to delete the node 21. Now 21 is childless, and so we can just take it away, just like that. We don't have to do anything other than remove the pointer from the parent node. But things are going to get a little more complicated if we want to delete a node that is higher up in the structure and actually does have children. So let's try this with deleting the node 27. What we're going to try and do, we're going to try and delete the 22. 27 here is the parent, that's why I've labeled it P. So to do that, the first thing we're going to need to do is to swap out what was previously 22 with 21, because we're not trying to delete 21, we're only trying to delete 22. So what we have to do is we have to take 21 and reattach it to the parent there. And notice that we only have to do that in this case to the left because it was a left child to begin with. And so we can do the same thing, breaking it up for the case where it's on the right. So if there is no right child, we have a case, and if there is no left child, we also have a case. If it has two children, that's where we run into some trouble. So if we have two children, then let's step through the case. So if we have two children, what we're going to do is we're first going to find the successor of the node we want to delete. So that's the next higher element. And so in this case, that is going to be 34 over here. Now what we do is we set the current node to be this. See, we swap the current node and the successor up. So swapping 33 with 34. And now the 33 is still what we want to delete. Because we said we want to delete 33, but what we're doing, we swap it with its successor. And now we do this again. We figure out the parent. We set the node that we want to delete to be 33. We swap it with a child because now we only have one child. And so now we can do the same process we did before and swap the bottom node out with the one immediately above it. So if you have two children, again, let's run through that one more time. If you have two children, find the successor and swap it, and then recursively run the delete procedure. So now in this case, we only have one child, and when we have one child, it's the easy case. We just swap it up into the right tree. The correct tree, I should say, not the right tree. So if it was a left child after, be swapped to attached to the left. If it was the right child, be attached to the right. And now it's successfully deleted the node. So now let's take a brief look at how we're going to implement this in C. And the good news is this is very, very similar to what you would have done for linked lists. And so just like when you need to use linked list code in this class, we've given you the list ops.c, we're going to give you tree ops.c for every time you need to use a binary search tree. And it's only in further classes that will actually get you to write your own binary search trees. So this is a version of treeops where I've also included the deletion code. Deletion code is more advanced because we saw we had those extra cases, like what if it has one child on the left, what if it has one child on the right, and what if it has two children. So even in the normal treeops that gets distributed for this class, we don't even have deletion, but I want to show you the full one. So just like with a linked list, just like with the linked list code for the class, we're going to have a tree_t type that's going to keep track of the tree overall and just keep some helpful information. And that will have our root. So let's look at treeops.h. There's treeops.h. And this has our structures just like we had before. It has our tree t type. And now notice what we're doing this time is this time I've actually added a comparison function pointer in here so that in the void star type, we can store whatever kind of data we want, and yet we'll still always have a way to compare two nodes in the tree. That was what we talked about last time. We wanted to have some way for the function pointer that told you how to compare the data to travel with the data itself. So rather than making one tree that is a string tree and then having a special function search in string tree, instead we just have like a search function and we pass it the comparison for a string tree. We pass it the comparison function for an int tree. And so this is one of the reasons why we're actually going to use the technique that we learned last time in class. And then we just have some prototypes in here. So let's go back into our tree ops. Notice that our make empty tree takes in one argument. And this type of argument, what type of argument is it? Just shout it out. What's this funny syntax again? We just talked about it 2 seconds ago. Yeah, Finn's got it right. It's a function pointer. So this is a function pointer for the comparison function. So when you create the tree, you're going to specify what kind of tree it is. Is it a string tree? Is it an int tree? And the way you do that is by passing it an appropriate function pointer. And then once you pass it in, we're actually going to save that function pointer for later inside the tree itself. So when you're using the tree, you can now use that comparison function. So we'll have a function to check if the tree is empty. That one's pretty straightforward. Just check if the tree has a root. And here is our recursive tree search function. Now this is almost identical to what we did before. So first thing we're doing, we have a case now to check if there's a root. This makes the code a little longer. And now what we're doing, we're replacing our simple comparison before with using our comparison function pointer. So rather than just saying, is this bigger than 42 or is it less than 42? It says, use the comparison function to check if the item you're looking at is bigger than the item you're searching for, or is it smaller than the item you're searching for? And this is just going to use the same comparison function that we passed into the tree in the first place. Okay, so let's look at insert. Our insert is again the same thing as we just described. So if there is no root, make a new tree. Otherwise, use the comparison function to figure out whether you should go to the right or the left. And keep doing this recursively until you find the place for the item. And once you've found the place for the item, that slot will be null. And so return the item. So this was only a helper function because you'll notice that it needed to be passed the new item. So given that we're always going to be inserting the new node into the tree, this recursive insert function is going to take as one of its arguments the actual node that you're eventually going to place into the tree, which means we're going to need a helper function, an auxiliary function, that's actually going to do this, like join this process together of creating the new node, figuring out where it goes, and once you've figured out where it goes, actually putting it in. And so that's just what we're doing here. We're creating the new node, we're storing the value in the value, and then once we figure out where it goes, we're going to put it in that location and use a pointer to it. And I'm not going to go through the remainder, I think. Oh, yeah, I'll point this out briefly. So this is our recursive free tree. Where's traverse tree? Recursive traverse. Yeah, here is our traverse tree. And this is exactly what we said before. Let's say there's some action we want to do on every node of the tree. We can visit the left side, do our action, and then visit the right side. But you can also order this differently. It doesn't inherently matter if you visit the left child first and do stuff on the left subtree, or if you visit the right subtree first and then do things on the right subtree. However, play around with this. Maybe make the action that you're going to do, which here is a function pointer, something that prints the value of the current node, and see what happens if you change the ordering. So if you do the action on the... Here, I'll do an example. So I will play around with this yourself, but let's imagine we have the number 45 and it has a child there and a child there. Left and right. If we visit the left tree first, and then the current node, and then the right subtree, that's what we'll get. So now let's do this a little further and build out our tree more. Ooh. And I'm going to make that 7 and 49, and then let's make that 3 and 50. So now let's try printing out what will happen if I traverse always the left subtree first, then the right subtree, and then the root itself. So this is still trying to autocomplete things for me. There we go. Okay. So I'm visiting the left subtree first, which means the node I'm currently looking at is 12. Now I'm visiting the left subtree again of 12, and that's 7. So 7 is the first number that gets printed. Now I'm visiting the right subtree of 12, so that's 49, and now I'm visiting 12 itself. So that's the order I get. Now what I've said is I'm back at 45. And my rule was do the left subtree, then the right subtree, then the root. So what would I get? I wouldn't get 35 because when I select 35 as my new temporary root, then I have to visit its left subtree first. So I'm then going to write down 3. And then what number am I going to write down next? 50. And now 35. And finally, I'm back at 45. So you can see that depending on the order in which you visit them, you're going to get a different output from printing, and you'll get a different arrangement of your numbering. Now, I would also point out for all of you in the room that this is a pretty good exam question to do to test whether you understand binary search trees, is to see, like, can you get the order of traversal right if we give you a tree and tell you the order in which things are visited? Is it left subtree, root, right subtree? Is it left subtree, right subtree, root, or some other ordering of it? Okay. And then the last thing to show you is just an example of actually using this. So this is going to use a binary search tree to count words and then print a sorted list of words and their frequencies. So you've seen this example before in lots of different guises, but now we're just using a different data structure to do it. And the reason this is going to be efficient is because rather than getting all the words and then sorting them, we're actually going to update as we go along by virtue of the fact that the binary search tree makes that pretty efficient. So we have a function to compare parts of a string, to compare strings. We have a function to print our tree, which we're going to want. And then this is kind of where the magic happens. So same structure as we've seen every time that we've done this task before, except now we're using treeops.c, and you'll see at the top, we've included treeops.h, which is this function that includes all the treeops. Where was it? Tree, e.g. Go, we're going to make the tree, and for each new word that comes in, we're going to search the binary search tree to see if that word is already there. If that word is not in the tree, then we're going to add it. And if it is already in the tree, what we're going to do is we're going to use the data element within our node to keep track of how many times it's been seen. So now we have this structure that's doing two things for us. Not only is this structure keeping track of what words we've seen before, it's going to keep track of how many times we've seen it as well. And then all we have at the bottom is traverse tree. So let's see if I can compile this successfully. Clang. If my compiler decides to wake up today. I know lots of us in the audience are tired, and it seems my computer is as well. Okay. So, oh, it wants my other C file. It wants treeops. And now it wants getword.c, which I might have forgotten. Oh, getword.h. And getword.c, sorry. So that time it worked. Essentially, the issue what was happening is I'd used these functions that I hadn't actually included the code for. So I had the prototype for the function, but the linker, which is part of the compiling process, looked to see if I'd actually written the code that I'd said I was going to provide, and I hadn't provided it. So what I needed to do was I needed to add to my compiler references to those other files where that other code was present. And the way I did that was just by including those additional C files, all of which were getting compiled together. So now I have tree.g and should be able to run it on moby alpha.txt. And there I can see that it's read in all the words in Moby Dick and printed out their frequency. So U appeared 851 times, Yorkshire only appeared once. And you can play around with that, and it's quite fun. So that concludes our discussion of binary search trees, but we're still not done with all the data structures for the class right yet, because we still have a few more questions that are going to be asked by our ape that we want to know. And we want to know not only can we do this by brute force, but can we do it efficiently? So using the same data set, we now have a different question. How old did Mojo Jojo live? Now, who here has programmed in Python before? Put your hand up if you've done Python before. Okay, so almost everyone has done at least a little bit. Where is the microphone currently? Sharon's got it. Do you want to pass it? Guy in the hoodie, I can't see who it is. What was your name again?
Venera.
Venera.
Yeah.
Okay, so what would you do in Python to figure out, to solve this kind of problem? So if we had a whole set of apes and their ages, and you wanted to figure out, okay, if for this ape, how long did they live? For that ape, how long did they live?
Would dictionaries work? Dictionaries?
A dictionary, yeah, that's exactly right. And so that's going to be what we'll talk about for the next little bit, is how to create a dictionary in C. Now, what kinds of properties do we want in a dictionary? What kinds of things do we need a dictionary to be able to do to be useful?
Store two things. Store two things.
So it needs to store stuff, but what functions do we... Let's say we start with an empty dictionary. What functions do we need? Is an empty dictionary much use?
No.
So what do we need to be able to do?
Input data.
So we need to be able to put things in, so insert. And data for a dictionary comes in what form? Is it one thing that we put in a dictionary at a time?
Multiple.
Multiple things. So what do you call that in Python? Do you remember?
Polymorph. Oh, in Python.
Maybe you don't remember. Key and value. So we have, if we want to know the age of every ape, so we'll have the ape is going to be the key because that's the thing that we want to look up. Sorry. We want to look up the information for every ape, and the piece of information associated with it is the age. So the ape is going to be the key, and the age will be the value. So that's one of our functions. What's the other function we need? So now you've filled it. What do you want to do now that it's full? Are you done? You're just going to leave it there on the side and forget about it?
Is it the comparison?
Kind of. What do you actually, why did you get this thing in the first place? Why did you build it?
To store all the ages of each of the monkeys.
But you've stored it, so that means that you're probably going to want to...
Look at it as well.
Yeah, you're going to want to look at it. You're going to want to retrieve things. So along with insertion, which we're going to want to do a lot of, we're also going to need retrieval. And we also want that to be fast. And those are our two key operations, and then deletion is the other. So maybe we're going to want to remove items as well. So this is how to implement the running time that it would take to implement a dictionary, given all the different data structures that we have so far. So you could do this with just a random array. You put all the items in the array, and it only takes one step to insert because you just put it at the end of the array. Then every time you want to find something, you look through all the items in the array, and you check. Is this Mojo Jojo? Is this Mojo Jojo? Is this Mojo Jojo? And that takes O of n. And then to delete, it's the same thing. You have to look all the way through for the item you want and then remove it. So not great. Okay, what about a sorted array? Well, insertion is going to take O of n because you need to find the right place in the array to put it in, and then move the things to the side and do the copy of the items. Remember we did that whole thing with Sarah where we had to like copy her over if we wanted to change the ordering. If we wanted to fix the ordering in a queue, same kind of thing for a sorted array here. Then search, we can do log n, that's our binary search. And for deletion, it's the same thing again where you remove it and then you fix up the ordering of the sorting. We could also do this with a linked list. That makes insertion really fast, but then we have to go through checking all the links over n time to find the right one, and deletion is going to be the same kind of thing. We could do a binary search tree, which is what we just looked at, and then the worst case would be O of n insert, because that's how long our insertion algorithm takes. O of n search worst case, and then O of n deletion. So that seems really bad, but on average case we can do a little better because we know that most of the time when we have a balanced binary search tree, that we're only going to have to do log n trips down the height of the tree. So that's okay, but always in this class we want to do a lot better. So the question is, can we really get that O of 1 that we see in some of the columns and put that in more columns? Can we do O of 1 insertion, O of 1 search, and O of 1 deletion? And that's going to be our next challenge. So I know you've all been getting tired of this apes thing, so let's go back to the Taylor Swift Eras Tour. And for this case, we now want to know which student had which ticket. The same kind of idea as which ape had which age. This time we're just pairing students with seat numbers. And so Alistair here has been the very lucky recipient of an Eras Tour ticket. He's got seat number 33, Claire is in 82, and Lou is in 75. And we're going to call this structure a hash table. It's a lower level version of what you'd call a dictionary, and it's going to be our implementation of a dictionary. So just like we said, you could do make a dictionary out of an array or a binary search tree. You can also make a dictionary out of a hash table, and this is going to be the thing that really allows us to get these powerful speed ups. And it was first created or first conceived of in 1953 by Gina Andal, Elena Groh, Arthur Samuel, and Hans Lund, who were all working at IBM at the time, and is one of the crowning achievements of basic algorithms and data structures. And with that, we will take a 5-minute break and come back to learn all about hash tables. Okay, welcome back everyone. Hope you had a nice break. We are now going to talk about one of the most exciting data structures, and this is probably one of the ones that you will use the most frequently in your career. Already, for those of you who've been programming in Python, you will have used dictionaries all over the place, and hash tables play a similar role. So the basic idea here is that we want to convert the key, the thing that we're going to perform the lookup based on, into an array index. So we're going to have an array that'll be what will underlie our hash table. And what we want to do is figure out which index in the array should we store this particular bit of information, and do so in a really fast way. So you could imagine that we could have different IDs of people, and then we could, and those would be the same as indices in our array, and then we could have different seat numbers. But this assumes that we have some easy way to map the keys that we want to use, which in this case will be the names of people, into the different locations. So if we had a way to do this really well, then our problem would be nearly solved. So essentially what we're going to want to do is have some function that takes as input the key and outputs the location in the array, or from now what we're going to call the hash table, that outputs the location in the hash table where we should look for that item, and where we should insert the item, or where we should delete the item from. So it's going to map a very large input space, so the space of all possible keys, into a much smaller output space, which is the space of all possible array indices that are valid for this particular hash table. So if we have a hash table of size 100 that has room for 100 entries, and we have names of people at most 4 letters long. Now I know that's a very small name, a small number of letters for a name, but we can see already that the number of 4-letter names is much larger than 100. And so what our function is going to have to do is it's going to have to map all of those names into that very small space. But the benefit is that most of the time we won't need to store every possible 4-letter name. There's only a small number of those names that will actually be used. So as long as we can ensure that the distribution of array indices that it outputs is more or less random, then we'll know that if we pick 2 random 4-letter names from the set of all possible 4-letter names, then the chance that they will collide and map to the same location in the hash table is pretty low. For example, let's take the name Danny and the name Shams. Danny and Shams, will run them through our hash function. Danny will say get index number 4, Shams will get index number 47, and that will be where we'll store the information for those people. And then anytime someone wants to look up Danny, they just run the hash function over that key over Danny, and they'll get back the number 4, and then they know at what index in the hash table they're supposed to look. So we can represent it this way. For a given key A, compute this function h, which is going to be our hash function, compute h of a, and that'll give us an array index t, where t is less than the number of possible items that the array can store. So again, if there are 100 slots, then t will range from 0 to 99 because our arrays are 0 indexed. And so what the hash function is doing is it's converting the key a into the number t. And then what we'll do is we'll just store the value corresponding to a at index t. So like Danny and 4, so Danny would be the value a, h of a would be 4, and then we might store Danny's seat number, which is 33, in location 4. So this is called a hash table, or alternately you might also see it called a hash map. And for those of you who use Java, Java frequently refers to this as a hash map. So the goal here is to ensure that the chance of 2 items ending up in the same slot is really low, and the way we do this is by making the hash function distribute items as evenly as possible. So there should be an even distribution of the keys mapping to the values. So every value that our function h can output should be equiprobable, uniformly likely, and not depend on the input. Now this second part is also important. We should try and break the connection as much as possible between the input and what the output is. So we'll talk about some bad hash functions in a little bit and why they're too closely connected between the input and the output and why that makes this difficult. So it's a trap. What if location T is already occupied? So let's say Danny and Shams both map to location 4. So there are a few strategies that we can use to try and help deal with collisions. So the first thing we could do is do a better job at hashing. So one way to do this would be to just design a better function h, or we could use a second hash function, and if they collide on the first hash function, use the second hash function, and if those 2 hash functions are designed differently, and they have this random distribution property, then the chance of them colliding on both the first and the second hash function should really be minuscule. The 2 other strategies that we'll talk about are open addressing, which is allowing items to leak beyond the location at which they were meant to be. So say you were meant to store it at location 4, or maybe we come up with a scheme by which it's allowed to drift into location 5 or location 6 if location 4 is already occupied. The other one is closed addressing, and this means even if 2 things have mapped to location 4, just find a way to store them both at location 4. And we'll talk about each of these in turn. So strategy 1 is chained hashing, which is just this idea of using a second hash function if there's a collision. So here's our hash table again. We have the keys from 0 to 5, and let's say we want to insert Chen, who has seat number 83 at the Eras concert. Is Chen here today? So let's say we insert Chen, and Chen is maps to index 1 through our hash function, and so we insert 83 at location 1 in our hash table. Okay, so we've inserted Chen into location 1. Now let's say we want to insert Ella, who has seat 99. But unfortunately, when we compute the hash function on Ella, it's also equal to 1, which is already the location that was filled by Chen. And we can see that because if we go to that location in the hash table, it's already full. So instead, we can have a second function, h2, and detect that that first collision occurred. And so we use our second function, and now Ella maps to location 4. And so we put the 99 in 4. Now, the problem is, you might ask, well, how do we tell when we later want to retrieve something if it's Ella or if it's Chen who is in that location? Does anyone have an idea of how we might solve that? So, at location 1, we could store one thing, or we could store 2 things. What other thing would you store at that location to let us know, to help us figure out whose it is? Yeah, the name. Not that bad. So if you store the name along with the seat, then you can tell who it was that was inserted there. Your lookup is still fast, but by storing this extra information, you've now allowed yourself to detect these collisions. The only problem is now the amount of memory that you have to use to store the table has gone up very considerably because you're storing both the key and the value at the location. So that's one downside here. Now, what's the expected runtime? Oh, yes. Jack.
How did Ella accidentally get mapped to 1 in the first place?
So remember, the input space for our hash function is really large, and the number of possible outputs is small. So by the pigeonhole principle, there must be some places where there are overlaps. So let me do an easy example. Let's say you have box 1 and box 2, and you have 4 people. And the rule is you have to have a function such that every person's name is mapped to a box. There's no possible way that every person gets a unique box because you've got 4 people and only 2 slots, right? So there must be some combination of people for whom you'll end up with a collision. The same thing is true of hash tables. You have a very large possible set of names and only a very small number of possible places where they could end up relative to the number of possible names, which means for some names there is a collision. Now, the goal of writing a good hash function is to reduce that probability as much as possible by making the likelihood of that happening low. A good first way to do that is to just make sure that the distribution is even. If you really were trying to optimize it more and you knew a lot about your data, maybe you could write a hash function that was particularly targeted to the distribution of data that you were expecting. But no one really does that, as far as I know, for most practical applications. So the question is, what is the runtime now of our hash table? So the big thing that's going to determine the runtime of our hash table is going to be how full the hash table already is. If the hash table is already very full, then our chance of having a collision is much higher. Like if you filled 99 out of 100 slots and you have a new person coming in, well, they're pretty much guaranteed to collide because you've already used up the vast majority of the space. So you can define the load factor, which is how many items you've put in as compared to how many slots you have, and we'll just call this alpha. And by doing some hand-wavy math, I'm not going to go through the details of it for you today, but you can view it in the slides. We're going to calculate the expected number of collisions that we have, because the number of collisions that we have is going to determine the amount of extra work we do every time we have to do an insertion. So you grind away, and it turns out that we can bound the number of collisions that we're going to get by the load factor in order to get our big O runtime of O of 1 plus a little bit, which is proportional to how loaded our hash table is. But for the most part, we're just going to write O of 1 and assume that we've made our hash table large enough that the load factor really isn't an important factor. So how do we do deletion? We talked about, Angela mentioned this before. We can just store a key at the destination along with the value so we know actually what item it was that we're looking at. So that's strategy 1. Strategy 2 is linear probing, where if we get a collision, just move to the next free slot in the hash table. So if location 2 is full, move to location 3. If location 3 is then full, move to location 4. And so let's do our example again. We wanted to insert Chen. Chen is at location 1, so that's all fine, no collision. And now we want to insert Ella, but we have this hash function collision. And now we only have one hash function in this model. This is a different strategy. So where do we put Ella? Well, let's look at index 2. That's full. Index 3 is full. 4 is full. 5 is full. So we wrap back around to 0. And we put Ella in the first free available slot. Now this has some of the issues that we've seen before in that now our insertion is not just one step anymore because we've had to go along until we've found the first free slot. And just like we saw before, the load factor is now going to be an important determinant in how long this actually takes. Because if there aren't many items in, the chance of us getting a run of like a lot of items in a row is going to be low, assuming that our hash function has distributed things well. However, if the array is almost full, then we're going to get far more steps. So Donald Knuth, who we saw in our start of our lecture last week, was the first person to do a formal runtime analysis of this, and he again found that it was proportional to 1 plus 1 over 1 minus alpha, which is essentially still O of 1, though it's going to get worse as you add more items. Alistair.
What's the benefit of this over like an array of structs? It's kind of like similar, kind of, you got a key.
So it's the lookup time. If, in most cases, assuming that there aren't too many items in there, it'll just take you one operation to go exactly to the item you want. So for example, let's say we want to look up Chen. We know that Chen hashes to 1, and so we go directly to index 1. We don't have to look through any of the other indices to figure out where he is.
The assumption we know that Chen's that one.
No, we know that Chen, the name Chen, we put it into the hash function. The hash function, which should be fast to compute, just gives us back 1 almost immediately. So this function, h, you're right, should run in O of 1, and that tells us where to look. So we don't have to look through all the places in the array. All we have to do is run this one function h. But I haven't yet told you how we make h, so it's okay to be skeptical that it runs in O of 1. But here's our real challenge. Is real-world hash functions are not truly random. We can't actually get this ideal perfect distribution. So how do we deal with this in doing our analysis? It's really complicated, but essentially for a real-world analysis, once we add a few more hash functions into the mix and combine linear probing with multiple hash functions, then we can get back to O of 1, essentially. The real-world performance is still going to be O of 1 in most cases, but the theoretical analysis is a little complicated. So what actually happens is real-world implementations tend to use 2 independent hash functions, or hash functions that are as good as independent as we can get, and then we just assume that the keys are not going to be, that the keys are going to have some randomness in them as well. So in actual practice, what's the upshot of all of this discussion? Hash tables are just going to be O1. And for deletion, how do we do this now? Well, let's say we want to delete Kevin. Kevin is in slot 4, so we can just delete him. But now, if we deleted Kevin without putting a tombstone or a ghost in the array, we would have the problem that when we tried to delete Ella, we'd look up Ella and see and go to 1, but then we'd go along and get to the space left by Kevin, and would see it's empty and would expect Ella to be there. Remember, linear probing is go in the full spaces until you get to the first empty space. And this is why we put the ghost there, so that we don't break the runs, so when we try and look up Ella again or try and delete Ella later, that we can still find her. Because if there was an empty space there, our linear probing strategy would say, stop when you get to the first empty space. So we call that a tombstone. So we go to Chen, U, B, we skip over the ghost, go to long, and then we get back to Ella and can now delete her, and we replace her by a tombstone. Now, the problem here is that this looks like a lot of extra work, but again, the analysis is going to eventually show that for low load factors, we still keep our O of 1. And now the very last strategy that we talked about, and this is separate chaining. And this one actually is pretty easy to conceptualize, probably easier than the other two. Actually, I lied. We have a fourth strategy I'll talk about very briefly. Our third strategy, separate chaining, is just to allow multiple items to be stored at each location. So this is where our linked lists come back in. Let's say we insert Chen into slot 1. What we do is we create a new linked list to store at slot 1, and Chen is at the top of that linked list. Now when we want to insert Ella, Ella's also at 1, so we go to location 1, go to that linked list, and go and insert Ella at the end of that linked list. Now, what is our challenge here?
If we have to search through a long linked list, so I guess it could almost turn into n squared depending on if you have a lot.
If you have a lot of things, then you would get an O of 1 lookup to get the slot initial.
Yeah.
And then what's the maximum number of items that you could have in the linked list?
N?
Yeah, so it wouldn't be n squared.
Oh,
You'd have O of 1, and then you'd go through a list of n items. But what's the chance of all of the n items being at the same location?
Low if you have
pretty
a,
low.
yeah.
So in expectation, we're really not going to get this case where we have these ultra long lists all at the same location, because the very design of our structure was to try and distribute them as evenly as possible. So this strategy is a pretty practical one, and also relatively easy to implement. You could probably do this in an afternoon. So now let's say we add Journey, and Journey has a seat number of, well, mess that up. Journey's seat number is meant to be 100, and she is in location 4, so we now have a second linked list there. And if we want to look up Ella, well, we hash her, we get the number 1, and then we just traverse the linked list until we find her. And then to delete Chen, again, the same kind of thing. We find what he maps to with the hash function. He's at location 1. We go to the linked list, and then what do?
Search through the linked list.
Well, we search through the linked list, and now we've found him. So what do?
Return.
Well, up there I said,
Oh, delete, sorry.
yeah. And how do we do that for a linked list?
Delete, then move the one below back up.
Yeah, so we're just going to set a new set Ella to be the new head of the linked list and free the memory. So not so bad. While we're at it, we need a round of applause for Hamish because he did a lot of work for us earlier in this class. Sorry for the delayed gratification. And the last strategy that we're going to look at is called Cuckoo Hashing. Now, who knows what is distinctive about the parental relationship in cuckoo families? Yeah. Yeah. So cuckoos are renowned for their somewhat violent behavior of nest stealing, and the same is true of our cuckoo hashing. So essentially the way cuckoo hashing works is you kick out the last item, and then you have a second hash function in this strategy again, and you insert the old item that was there somewhere else using that second hash function. So you have two hash functions. The first thing you do is you check if your item, if the first hash function leads you to a free slot. If it leads you to a free slot, no collision, nothing to worry about. If you have a collision between your two items, kick out the old item and use the second hash function to figure out where the old item goes while putting the new item in its place. If you get another collision, repeat this process. So if when you take that second item and that second hash function, you get another collision, do this thing over and over again, and then you get all these pretty pictures with poor birds being kicked out to different places in the hash table. So if you get a cycle, which is possible, where you kick out A and A kicks you to location B and B kicks you to location C, and then C kicks you to location A again, you've got a cycle. So then you rehash everything using the different hash functions. So what's our overall runtime for all of our different strategies? I've put them all up in this table for you that you can then take a look at. But at the end of the day, for the most part, we're still going to get O of 1 for everything except for the naive chaining strategy, where we get worst case of O of n, although those worst cases don't really eventuate. So the caveat is that cuckoo hashing is quite complicated and requires a whole lot of different independent hash functions, and that this is needed for linear probing as, not for linear probing as well. So the other caveat here is that you need good hash functions. And I've spent a lot of time saying, well, you need hash functions that have these random properties, but what does that actually mean? So one way to describe it is that we want to use all the different bits of the key. So let's say you have a name that's 4 letters. You don't want to do a hash function that just relies on the first 3 letters. Why not? Why would just using the first 3 letters be bad? Jack?
Lots of things share 3 letters at the start.
So for example, Dano and Danny, right? What would happen if I tried to put them both in?
Both go to the same, like hash.
Yeah, you'd get a guaranteed collision if you're not using all those bits, because things that share the same prefix bits will then share the same location, which isn't good. But you also want to try and check the distribution of the actual data that's going to be coming in, if you can, to design an ideal hash function for that. So for the most part, all the results we've talked about are only true when the load factor is very small, and we've also been a little lazier in our analysis. So there's new research that is still improving the complexity analysis of how these hash tables actually perform when the load factor gets high, and that's interesting from a theoretical perspective, but also from practical perspectives about like, how can we really maximize the space and time trade-off that we've got here. In practicality, mostly whenever the load factor gets high, you just make your table bigger. So for an example, Java rehashes whenever the load factor gets to 0.75. So when 75% of the spaces in the hash table are used, Java under the hood will automatically increase the size of the hash map. So if you look back to our table before, well, there we go. No. You'll see that kind of the best one here was Cuckoo Hashing. But there is a caveat. In practice, Cuckoo Hashing is slower than linear probing when you actually go and do the implementations. So it's not about the theoretical analysis in this point, which again reminds us of one of the lessons, which is theoretical analysis is important and gives you really important tools to analyze your algorithms, but you also have to combine that with empirical analysis of the algorithms to actually find out what will be good. So there are lots of improvements that one can make to the strategies that I've presented today. And there are ways that we could even improve, that you could come up to improve things like separate chaining. And so I'll leave that as an exercise for you to come up with a better way of doing separate chaining to make that more efficient. So one thing to know about this is that hash tables are what we call randomized data structures. So where does the randomness come from in here? Yes, Toby. So the key is one source of randomness because we are expecting our key inputs to form part of a distribution, but the same is kind of true for many other data structures. So for example, if we were doing that if we were doing a dictionary with an array, our keys would still be random, but that still hasn't made the array itself random. Where's our randomness coming from? Sarah? Yeah, so our design of the hash functions is really what we're trying to make random. We're trying to introduce a probabilistic distribution by using these hash functions. And this is going to lead to a whole new area of algorithmic analysis that you could study at the master's level if you wanted to, which is random algorithms that use randomness and data structures that use randomness to try and improve their properties. So so that wraps up most of our discussion about hash tables. So we're now introducing data structures at you really, really quickly. I will also tell you that for the exam, you're not going to have to know all the details of the complexity analysis of all the different chaining strategies. What I would expect you to know how to do is, if we give you a hash table, like one of the pictures, to be able to draw out what would happen under one of the different strategies. So just kind of conceptually understanding it is what I'll help you do. The rest of that is just there for your edification. So now we have a new, I don't know what that placeholder is in the corner. So now we have a new Taylor Swift challenge. We're really on a roll here. I'm hoping she comes, visits for the last lecture of class, but no promises. So now what we want to do is figure out the most efficient data structure to distribute Taylor Swift tickets on the basis of grades. Now, I know I've already promised Alistair one, so maybe that means he's going to top the class. No? We'll hope so. But for the rest of you who are all fighting for the few tickets that I've got left, we need some new data structure to do this as efficiently as possible. So let's have some suggestions of data structures we might use. And if you already know where I'm going, don't spoil it for the class. But if you're just guessing, that's fine. Okay. Andy, you want to take first stab?
Sure.
What data structure should we use to efficiently distribute Taylor Swift tickets on the basis of grades, assuming that I have only a small number of tickets? Hold your microphone.
I do not know.
Nothing? Okay. What data structure could we use to distribute Taylor Swift tickets on the basis of grades? No idea. Okay. What data structures do you know? Probably know at least one. That's okay. Okay. Think of one data structure. We'll talk about a bunch today. We'll talk some earlier in the semester. A struct? Yep. So a struct is a good example of a data structure, but it's probably not going to be super helpful for us when we have large collections of people and their grades. Well, let me take that back. Structs will be absolutely necessary because the structs will link people to their grades, but they don't actually solve the problem for us of figuring out who has the highest grade. So we can start with a collection of structs. So that was a good idea. And run?
Yeah.
Run, yeah, okay.
Considering we were just talking about like hash tables,
Hold it up a little more.
hash functions, maybe something along because the way it's like a dictionary but in C, right? So that would help find
So sketch that all out a little more for me. So say I have Maya who's got 97 and you've got 98. How would we make our dictionary to figure out who had the highest score?
Well, the Python equivalent, you would like use the key to get access to the value and then you compare the two and whoever has the highest grade would get the ticket.
Yeah, but then we'll have to go through everyone, right? And we'll have to go through everyone and compare them. Anyone else have other ideas of things we could do? Pranav, I've already heard from you today. Okay, let's go. Amanda, was it? Unmute it. There we go. What's your ideas?
Hash table or like list.
So we tried the hash table. It didn't work so well. What about something really, really simple? If I want to find out who has the highest grade in the class and then the second highest grade?
Array.
An array. But what kind of array? Jay, you're giving it away. It's okay. So a sorted array would help. Now, what is the problem with a sorted array and removing things from the start?
In an array, you have to know the index, like how many elements are there beforehand, like you can't change it.
So with one of the things is like, you're very much on the right track here. With the array, we had this thing that when we deleted people from the front, then we ended up doing this like expensive copy thing where we copy everyone forward. But we had, I think, going back to Sarah earlier in semester, and maybe I'll pass the microphone to her. Thank you very much, Amanda. Sarah, I'm coming back to you because this was actually part of your demo when you were standing at the front, so you might have some memory in this. All right, what data structure was using? It was an abstract data structure, very similar to an array, or we implemented it using an array.
That one was a queue.
It was a queue. So a queue is good if the only piece of information that we need is when the person arrives. So it's first come, first served. But in this case, what's the difference? What's our ticket distribution strategy? Is it first come, first served? That's a yes or a no one. No, so what are we distributing on the basis of?
Highest grade.
Highest grade, yeah. So what we want to do is have some way of when someone comes in, what do we want to do with them? Someone new gets added to the queue. How do we figure out where they should be in the queue?
Like on the basis of their grade.
On the basis of their grades. Now, just for clarity, I do not value any of you solely on the basis of your grades. You're all wonderful people, regardless of what you get. I just only have 2 Taylor Swift tickets left. So they'll sadly have to go, whoever's joining Alistair will be on the basis of grades. Yeah. So what we want to do is we want to take the same ideas of our queue before, only we want to modify it so that when someone new comes in, they go to the right position on the basis of their grade, and then we can take people from the front of the queue who will want to have the highest grade, and keep doing that and do our removal from the front, and our insert is going to place them correctly. So that's essentially our idea here. We need something very similar to a queue, where we have an is empty, an insert, and remove, and that's all. That's all we need to do is solve this problem. So we're going to use what we call a priority queue. Now this is an abstract data structure, just like a dictionary is an abstract data structure. You can make one of these using lots of different underlying things. So what we were talking about just here was using an array as the underlying implementation for our abstract priority queue. Just like we saw that you could do queues with linked lists or arrays, likewise you can do priority queues with linked lists or arrays. It's possible to use many of your data structures, many of your concrete data structures, to implement the abstract data structures, and it's always a matter of figuring out which one will give you the runtime that you kind of want. So there's a very naive version of a priority queue, and let's give someone, last bit of class, someone a chance to come up with this on their own. How you feeling? You want to do it? Remind me your name? Nazim. Okay. So I'm going to give you, I'll give you a piece of advice at the start. We're going to do this easy version with an array. And the property we want is that whenever someone new comes, they should be at the right place that reflects their order in terms of where they are grade-wise relative to everyone else in the array. So what is the stupidest and most obvious way to do this?
So when the first person gets put in, he's at the start of the array.
Okay.
And then when the second person gets put in, we compare their grades. If it's less, we put him after the person. If it's more, we'll put him before the person.
Okay, now let's say that's good so far. That's the right answer. Now let's say we have 10 people. And a new person comes along.
We do the same thing, but we have, instead of just comparing with the first person, we have to compare with, say he's less than the first person, we put him in the, we compare him with the second person. And then if he's more than the second person, he's in the right place. If he's less than the second person, you'd have to keep doing it.
Okay, you've given me the idea. We're not going to run through all the 10 people, but you can figure out where to place them by doing a linear search through the entire priority queue or the entire underlying array and figuring out the right location to use. There is an even stupider version, which is this one. Sort everyone in the queue. If someone new comes, sort the queue again, give tickets from the front of the queue, and then when you remove someone from the front, sort it again. So this is a pretty bad version because we know sorting takes how long on average case? N log n. So this is doing n log n every time, which is pretty bad. So this version was slightly better. And essentially it was this naive version too. If someone comes, fix the slightly unsorted queue, give tickets from the front of the queue, and then we're going to fix the slightly unsorted queue again. How long does it take to fix the queue in your model?
Would it take? So it takes n. If n in the worst case, if you have to go all the way to the end of the array.
Yeah, so big O of n is going to be a fix-up routine, which is not bad. So we can go from log n plus n in deletion to O of n, and then we can go with an array. And if we were doing the same thing with a linked list, we can do similarly O of n time. Now, the nice thing about doing this with a linked list instead of an array is what happens when we want to remove someone from the front.
With the linked list, you can delete someone at the front.
Yeah, you just delete the person at the front and make the head the second person. which would be array. This was again the thing we did with Sarah, who I keep bringing up the whole semester, where we had to copy everyone along again every time we deleted someone from the front. So that's not so bad. Plus we have to do an initial big O of n log n initial sort on the items that we start with. So even if the linked list is bad, we're adding items to a long queue. So we could also try attempting to implement this using a binary search tree. Would be another way. So let's take a look at our binary search tree behavior. So if we want to insert something into a binary search tree, we can always do that in log n time, and we can insert worst, and our insertion of worst case is log n time. To find any item in a binary search tree is log n time, but this is really where the exciting thing is. What about finding the maximum item in a binary search tree? So the way we've been doing it so far is that you go through the binary search tree and you figure out, you go down the height and find the largest one. But if we know that the operation that we're going to frequently do is finding the max, well, every time that we either insert something or delete something, we can just keep track of what that maximum is. Because every time we insert something, we'll know for sure if we've just inserted the maximum item, because that will have gone all the way to the right. Likewise, if you wanted to do a minimum version, like making a version that where the tickets go to the person with the minimum grade, you just reverse it. So you can keep track of, depending on the path you've taken, have you just seen the maximum item. So this allows us to do a 1. Yeah.
Did you never insert an item that's larger than what's already existing? That doesn't work.
You never insert an item.
Yeah, so like
So this assumes when you created it, you've also kept track at the end of the creation. Yeah. And then we also have creation is n log n for our binary search tree, and delete is log n. So we've already improved by switching which kind of concrete data structure we're using to implement our abstract data structure. And this is going to be one of the really cool things that you guys are now able to do, is I've given you a whole bunch of different concrete tools, and using those to tackle different problems, you can think, okay, what is the abstract kind of thing I need to do at a high level? How would I implement that with different concrete data structures that I've got? And what would be the runtime if I did it this way or if I did it that way? And is there a tweak I could make, like this caching thing, which caching just means to save something? Is there a small change that I could make that would improve the behavior substantially in combination with one of the data structures that I've already done? So that was pretty good. We've already improved on things, but we can do one better. And this is where we introduce a heap. And I think we are almost done for today. And so we will carry on with heaps next lecture, and you can all go out a few minutes early. Thank you, everyone.